Thanks so much for having me here today. I'm really excited to talk about some of the research that we've been doing, and hopefully it's of interest to a lot of you that are here. I kind of want to give just some high-level overview around the philosophy of some of the research I've been doing, and specifically this most recent paper, Style Transfer of Audio Effects with Differentiable Signal Processing. And this was work alongside with Adobe, where I was working with Nick Bryan and along with my PhD advisor, Josh Reiss. So yeah, let's get into it. So first, just a little bit of background about myself for those of you who don't know me. Currently, I'm a PhD student at Queen Mary University of London, where I'm doing a PhD in AI with applications in audio and music. And before that, I did my master's at UPF in Barcelona, studying sound and music computing, and did my bachelor in electrical engineering and audio technology. Outside of my research, I kind of got into this field partly because I was an audio engineer doing mixing and mastering, and also because I studied that in my bachelor. And so a lot of my research has kind of been inspired by trying to find ways that AI can help audio engineers. And in addition, I've done some internships, had the opportunity to do internships at some really great places like Meta, Adobe, Dolby, and Bose, doing research like this stuff I'm going to talk about today. And yeah, also follow me on Twitter at csteinmetz1 if you want to see what we're working on after this. But the main motivation for a lot of our work is the reality that more people are creating audio content now than kind of ever before. Whether that's kind of like in audio first applications like music or podcasts, but also huge growing areas like short form content and also just sound for video on platforms like YouTube. Kind of having high quality audio is something that's important across all of these different applications. And so the demand for kind of producing high quality audio is something that's on the rise for sure. And traditionally, to get high quality audio, you might have had a recording studio, something like this, a bunch of expensive equipment like condenser microphones. But now a lot of that's changed, and there's an extreme amount of power inside just a laptop and something like a USB condenser microphone. So the capture part of audio has progressed a lot. And there's also a lot of tools now in your computer to process audio. But unfortunately, it doesn't really end at the capture phase to make high quality audio. You have like a bunch of complexity from different plugins and DAWs that all have, a multitude of options and their own kind of learning curve in order to make some production, especially when you start considering multi-track productions, right? And if this, if this hasn't convinced you, producing high quality audio, as I'm sure many of you know, requires a lot of expertise. And if this hasn't convinced you, I really like this YouTube video from Jacob Collier where he breaks down one of his Logic sessions here, which you can see just has an absolutely insane amount of tracks. So the complexity of trying to build and mix something like this, I think, is quite extreme. So to bring it back to the research side, there's been a lot of really interesting development happening in audio and deep learning in this kind of what I call audio processing kind of tasks, where you kind of have this audio in and audio out with some neural network processing that audio. And this covers tasks like source separation, speech enhancement, or also audio effect modeling. But the current paradigm is that we kind of carry out these tasks using a large neural network in most cases that kind of is, maybe it's a convolutional network, maybe it's a recurrent network, maybe it's a transformer. But basically that there's kind of like just this giant neural network that we're training end to end to do this audio task without any kind of inductive bias. And these models can do some really impressive things like source separation, but they tend to require a ton of compute and tend to also add artifacts, which is something that us audio engineers don't tend to tolerate. So one of the major realizations or our viewpoints on this problem from the research direction is that audio engineers are already solving their problems day to day using DSP. So using different plugins or using other algorithms that have been designed by audio software developers. So for example, that's things like maybe how a guitarist might configure different guitar pedals to get their guitar tone. We can model acoustic spaces using impulse responses. So we can create high quality reverberation and make two spaces sound the same. Or even this kind of holistic task of creating a mix using a DAW and a bunch of different audio effects together. And so that really motivates our framework here, which is that we essentially want to build neural network models that actually control DSP, which is a different paradigm from this kind of traditional end-to-end neural network that does all of this processing. And so in this setup, we have some audio that goes in, but a neural network analyzes that audio, and then instead of processing the audio to make the output, it just generates some control parameters to modulate, existing signal processing devices in order to process the audio. And there's some main questions here that we need to answer from the research side. How do we integrate DSP with neural nets is a huge topic in itself. And then also another really important one is how do we convey, user intention to this system? How is, how we set up the training, in what data sets we use, and how we're going to do all of that. And so differentiable signal processing is the main technique that we can use to answer this first question. Yes. And this is kind of my diagram here of the general case that I look at it, where to formalize it slightly, it's that we have some deep neural network that sees as input some audio signal, and it's going to generate some control parameters, p hat here. And that those control parameters are sent to our DSP along with the input audio signal that's going to produce some output audio. And then what we want to do is we have some data set that we assume where we have like these input-output pairs, and essentially that's what we want to learn, this mapping between X and Y. And so then we compute some loss function potentially in the audio domain, and then we compute gradients, but we notice that we have to backpropagate through this DSP in order to generate gradients to train our deep neural network. And unfortunately, this process is non-trivial, and I'll get into that in a little bit about how we address that. I think just a few more points here on, to motivate you if you're not fully convinced yet, why do we even want to deal with this, having to solve this problem of backprop through DSP? Why not just use, a giant neural network to solve all of our problems, as is often the case? Well, I argue there's a lot of good reasons why we want to do this. For example, leveraging all of the existing DSP tools, I think, is more than enough of a good reason to do it. We have many plugins and many software, audio algorithms that exist already that are we throw out the window whenever we just use a giant neural network to solve those problems. Also, as I mentioned before, we get high quality audio since this DSP can run at arbitrary sample rates and has a very low likelihood of adding any artifacts. And also, really importantly, generally this P here, that's the parameters that are generated, are human understandable, right? So it actually means that this kind of paradigm enables audio engineers or users to go in if they desire and actually change how we might be able to how users might be able to interact with this. And it also can run efficiently in real time on CPU because the DSP is highly optimized for this kind of inference. And on this second point of conveying intention, I think there's a lot more to be discussed here, but just some of our way of addressing it in this particular approach. What that looks like right now is when you use a DAW, you have a plugin or you have some UI and you control some little knobs or something like that. And that's how the user conveys their intention, which, while it works if you understand all the knobs, it has a high learning curve and is generally not, I think, the ultimate goal. Obviously, as I'm sure many of you are also aware, text-based prompts are making have made a huge impact in the vision space right now. And so I think you could also imagine, well, maybe we could have something like that for audio, type in a sentence and that's going to configure my EQ. And I think that's a very interesting direction, but we actually suffer from not having sufficient data to actually build systems like this so far in the context of audio. Unfortunately, we don't have a giant data set, that describes how things sound, especially at a kind of audio production level. So what we aim to do in this paper is actually to take this approach of conveying intention by example, so that the user could actually supply some recording that they could use as a reference, essentially, which we also kind of call style transfer in this case. It's kind of similar or analogous to the image style transfer case, but in this case, we kind of can use another audio example that the user provides as this kind of by example case. And so what that looks like in our setup here is that we imagine that the user has some recording that they make, let's say on their mobile device. and they want to configure some kind of traditional audio effects to make their voice sound more produced, like an EQ and a compressor. And they have some reference recording, for example, let's say their favorite podcaster or something like that, or streamer that has some signal chain. So then we can introduce our model here that's going to analyze both the input recording, create some representation, and then also analyze this reference recording, create another representation, which then get passed to some controller neural network that can actually directly predict parameters for these different signal processors such that the input tries to match this output in the terms of the audio effects. So I have some examples of audio of the system working here to show you what it does, but I haven't successfully gotten my sound to share. So I'm just going to drop a link here to the YouTube that shows it. So if you want to take a quick listen to that, you should be able to hear it. But I'll give you like 1 minute to listen to that, but you should be able to hear a quick demo of what the system does when it's operating in this kind of style transfer setup.
Yeah, I know that my audio works when I share a video, so I can share this.
Yeah, that would be great.
Give y'all a second to join my stream. All right, here.
Yeah, you can go ahead and skip to like 1 minute in. Yeah. Yeah.
Populous kennels. The input speech again.
Oh dear, I shall be too late.
And the stylized output.
Oh dear, I shall be too late.
We can view the predicted equalizer and compressor parameters that were applied, refine the results, or simply learn how the transformation was made. In this case, low frequencies were boosted, high frequencies were
Cool,
down,
I think that was
a light amount.
Yeah, so hopefully in that very short example, you could hear what the system was doing there, right? Like the original recording kind of was lacking any kind of low end, had no compression on it. And our reference recording was a very produced recording. And it was able to kind of capture some of the style aspects there. We also did experiments on music, which you can also check out on our webpage that has all the listening examples as well. So I won't play it for you now. But we did experiments on both speech and music with this kind of same setup. So now let me kind of tell you, well, how we went about actually building this kind of model. And I think the idea here was that we realized that it's generally very difficult to kind of have paired data where you have the original unproduced and the produced recording. And so that motivated further this kind of way to do a self-supervised training with the style transfer setup. And we realized that also you could kind of view the audio production process as a three-stage process. And in that way, the first thing the audio engineer might do is listen to the recording to kind of understand what are its deficiencies, how might it be different. From that, they're going to create some plan or a goal, essentially, where they're going to decide what is the style, in quotes, in some sense, that they want to achieve. It's kind of implicit, right? But they decide what they want. And this is a really complex decision, right? There's not one, it's not a one-to-one mapping, and it considers the context as well. And once they've decided that, they're going to then manipulate ESP in order to achieve that goal. And so what we realize is that it's really the second part that makes kind of end-to-end modeling of audio production very challenging, because this planning phase is kind of implicit and ill-conditioned if you try to just train a model, like let's say a regression model, to kind of predict an improved recording that's produced or something like that. And so basically what we do is kind of take this second step out and make it part of the style transfer process, because then the user is the one that's kind of supplying the plan via this reference recording. And then the system only needs to learn how to do these steps 1 and 3, which is to listen to the recording and then execute the plan that's given by the user. So what that looks like more concretely is something like this. And this is like how our training framework and our model architecture fit together for this task. So we start with some data set of audio that can be any kind of audio. It doesn't need to be produced or clean even. So we kind of look at a few different data sets for that. Then we apply some very basic data augmentation like pitch shifting, time stretching, stuff like that. And then we pass it through a shared DSP chain in which this DSP has the effects configured randomly in two different ways. So kind of two different random configurations of the DSP, where, for example, the DSP might be an EQ and a compressor. And this gives us two different views of that recording, one that will become the input and one that will become the reference recording. And then what we do is split these recordings in time into an A and B section. So like the first half of the recording becomes the A section and the second section, half the section becomes B. And then what we do is swap these and pass them to our shared encoder setup so that the top branch of the encoder only sees the A section of the input, and the bottom branch, which is the reference, sees only the B section of the reference. So the idea here is that the encoder can't just assume that the content is going to be shared between the reference and the input recording, because right at inference time, the reference recording could be coming from any other type of signal. So this is kind of like a trick in order to encourage the model to not pay attention to or not assume that the content is going to be the same between both of them. And so then these are just simple convolutional encoder that operates on a Mel spectrogram, which then generates us these two embeddings that we can concatenate into a single one, which then gets passed to our controller. And our controller network is another simple neural network, could be an MOP that predicts some parameters to configure our audio effects. And that's where our then differentiable audio effects come in, which are some function of both the input audio and the parameters, which then generates, we pass in the A section into this, into our differential signal processing effects. And we can then use a loss function that operates in the audio domain directly. So this could be something like a multi-resolution STFT loss, for example, where interestingly we now have the ground truth because we generated this A section before, but we didn't pass it to the encoder. So we actually have a paired ground truth that we can use to generate gradients here to train all the way up to the encoder as well. So this kind of gives you a brief overview of kind of how the whole system can work. So I want to talk a little bit now about differential signal processing, how we enable that, because it is key to our approach. And just to give you a little bit of background on kind of the existing approaches and why it's more complicated than you maybe originally thought, and where the unanswered questions are that we investigated in this work in that context. So the predominant approach for doing differential signal processing leverages automatic differentiation. And I think this was definitely popularized in the DDSP paper. And the idea here is that you simply take whatever DSP that you want to backprop through and just implement it in your favorite autodiff framework, whether that be PyTorch, TensorFlow, or now JAX maybe. And you basically have this really high cost of implementation time. And it's kind of like what I would consider a white box method. You have to re-implement from the ground up every audio effect that you want to be able to backprop through. And this is a non-trivial task as well. But the thing is that if you can do it, you can get gradients for free because Autodiff will be able to compute them for you in most cases. But I was also interested in other approaches. So in some of my previous work for my master's, we looked at this neural proxy approach that we came up with. And the idea here is that similar to audio effect modeling, you first pre-train a neural network to emulate your DSP, whether it could be an audio effect or a chain of audio effects even. And in this neural network, you pass audio and the parameters of the original effect, and you just use some loss to try to minimize the difference between the output of your neural network and the real effect. And then what you can do is come back to our controller setup where we want to do the differential signal processing, and we can simply just take our frozen pre-trained neural proxy and use it as a differentiable proxy of the real effect, because now we have a continuous function that is ideally behaving the same as this original audio effect. And this is what we had investigated previously, but it's pretty challenging and doesn't fully solve the problem, unfortunately. Because what we really want to do is we really actually want to do what we call these neural proxy hybrid approach. Because what we really want is that during training, we use this neural network. But then what we really want is that inference, we want to replace it back with the original audio effect. And the thing is that we hadn't actually tested this before. And so in this paper was the first time we tried this. So essentially you train the main deep neural network with the neural network proxy, and then at inference time, you replace it with the real DSP again. But there was an open question here of how close does the neural proxy need to be in its behavior in order for this approach to generalize. So that's something I'll talk about in a bit. But there's one other approach here that's also interesting that was proposed by Marco Martinez et al. In their ICAST paper, where they actually are inspired by finite differences, which lets us kind of do a computational approach to estimate a gradient. And you can actually do this on DSP, and they do it in a more efficient manner using this approach called SPSA. And the idea here is that, if we can just estimate the gradients here instead of actually having to explicitly calculate them, this will really give you a way to potentially train this deep neural network. But from all of this, I've just given you a ton of info about how all these different methods work. And these are kind of the four main existing approaches. In this paper, one of the main things we were looking at is, there was no existing comparison of these different approaches and how they compare in an actual use case, because each paper had kind of used them in a different disparate task. So here, what we aim to do is implement our EQ and compressor using all four of these approaches and compare them head-to-head in a shared task of the style transfer of audio effects, which would give us insights into which ones might actually be the best one to move forward with. So we trained a bunch of different models to investigate this, including two baselines. One, which is a rule-based DSP approach. So we kind of came up with a rule-based system to do kind of style transfer of the EQ and compressor. And then we also have kind of as a deep neural network baseline, a conditional TCN. So we actually replace the DSP with just a fully free TCN that is trained to do the style transfer. So it's not actually using any DSP. So in some sense, that should be even more expressive than our DSP approaches. So we wanted to see that as kind of a baseline on the other side. We use multi-resolution STFT to train all the models, and we do experiments over speech with LibreTTS and music on MTG2Mendo. And we also consider a bunch of different metrics to understand the performance, and I won't go through all of them here, but just kind of show them really quickly. And the main thing to take into account here is that we look at some metrics that kind of are full reference and get the general similarity. But we also look at kind of comparing higher level features that try to capture things about the spectral balance as well as the dynamics in our case. So there's a ton of experiments in the paper, but I'm just going to kind of give you the highlights here. So what we found in evaluating these different approaches, there were kind of some really clear trends in how these different methods worked on the style transfer task. So the first thing to note was that the rule-based DSP was outperformed by basically almost all of the learned approaches. So it's a really good indication that our approach is warranted in trying to use a neural network to do the style transfer task. What we did find, though, is that the neural proxy hybrid approaches, this idea of like train with the neural proxy and then swap back in the DSP, didn't really work well. And that's what you can see here is that the PESC scores were significantly the PESC scores were significantly worse in the neural proxy case, and they were actually better in these hybrid cases, but all the other metrics were worse. And so we found that the neural proxies essentially didn't really work well. And it's likely due to the fact that there's a big difference between the real DSP and the best neural proxy that we were able to build. So even when we train the neural proxy with essentially unlimited data of the real DSP, the neural network still doesn't fully capture the behavior. What we found was that the gradient approximation approaches were quite good. That's the SPSA here, which outperformed all the rest, outperformed all the neural proxy ones. But we found that it struggled with instability when training. So we had to kind of do a lot of just tuning of the hyperparameters just to make it train stably. And finally, the automatic differentiation or AD approaches here had almost the best scores across all of our metrics. So it was kind of clearly the best winner. Interestingly enough, even outperforming the full TCN neural network-based approaches. So the AD approach, it has no learnable parameters. It's just the EQ and compressor that's implemented in PyTorch. And so it was actually doing the job better than a neural network that was trained, end to end to do the same task. So I think that was a really cool result. But I think we'll mention, though, that the biggest limitation here is that our AD effects are really only an approximation of the true effects because we have to make a bunch of tricks and hacks in order to make them differentiable. So there's kind of a big trade-off here. And unfortunately, these results, while I think AD is performing the best, unfortunately, it's not the most ideal method because it kind of requires that we re-implement all effects from the ground up in order to use them in this framework. So I want to talk quickly about a few other experiments we did that I think are interesting. So to further evaluate our system, we built a very simple data set, kind of like a production style. And so what we did is we defined styles by hand that were kind of meant to be as different as possible from each other sonically and kind of to be canonical style. So we have like a telephone sounding style, a bright, warm, a broadcast, and a neutral style, which instead of them being fixed presets, they're actually distributions within the parameter space of the EQ and the dynamic range compressor. So these are like sampled from those distributions, for example. And the idea is that, by defining these distributions, we can then sample many different parameters that all kind of sound the same, but don't have the same exact parameters every time. And then using this, we can take a data set of clean audio and simply randomly sample these effect parameters and generate a data set across these 5 different styles that we created. And the idea here is that they would, again, be kind of maximally different from each other. And so what we found from that is we ran the same kind of experiment as before, where we did every pairwise comparison between going from one style to the other style. So for example, take all of the bright recordings as the input and use the produced recordings as the reference, and vice versa. And then we could compute average scores from the high-level features across all of those. And we saw kind of similar trends as before, where the 80 approaches were the best, SPSA was second best, and neural proxy hybrids were the kind of the worst across all of them. But basically, this was kind of like a real test to see generalization, what would happen when the reference recording had totally different audio content than the input recording. And we had one final experiment here that I'll talk about, which we use the same data set that we've built here. But what we do is we take our pre-trained encoder and we freeze it and use it as a feature to use it as a representation for audio production style. And simply, as is often done in other self-supervised approaches, we just tack on a linear classifier at the end, a linear layer, and train it doing a 5-way classification to see, can we get, is there information about these different styles that were never trained explicitly, with this model to predict these. And we also compared against other audio representations. So, for example, CD-PAM is an audio quality metric representation, and also kind of OpenL3 is kind of like a standard audio representation that's not explicitly encoding quality. And what you can see is that, for example, OpenL3 kind of totally fails to capture these different classes, kind of indicating that it's learned nothing about production style. And that makes sense because these models are generally trained, with data augmentations to make them invariant to these exact things that define style, like, for example, the EQ curve and the compression. We found that CD-PAM was significantly better than OpenL3, but still way worse than our model. Only had an average F1 score of 0.73, whereas our best models could get actually perfect accuracy on this test set using only 100 examples here. So I think this was really interesting results, saying that beyond just the style transfer, these audio representations might be able to be used for different things. And we saw a pretty similar trend when doing this same kind of experiment on music as well. So as I start to wrap up here, I want to give some insights into things that I think are interesting to continue on this work. We've kind of just only started to scratch the surface, I think, on some of these directions. So I think the most obvious one is to simply extend our style transfer setup with more effects. Easily reverb or distortion could be really great targets here. You can imagine that being useful for like matching someone's guitar tone, for example. Also, there's a lot of benefits of this proxy method because it's a black box approach. We don't have to re-implement the effects in PyTorch, but it doesn't work well. So we need to figure out how to make that work better. I think something else that would be really interesting is dynamic construction of the processing chain. So here we kind of fix the EQ and compressor, but what if you had 10 different plugins and you wanted the model to be able to dynamically construct a graph of audio effects? Or adapt it to the multi-channel case for multi-track mixing? Or even, I think, the holy grail problem here would be, could you make an algorithm that can kind of zero or few shot adapt to a new set of audio effects and control them, even though it's never kind of been trained explicitly on them? So also I mentioned that all of the code for this in our experiments is totally open source, and you can check it out on GitHub. There's also a Hugging Face demo that lets you run some audio through the model as well. It's not fully featured, but you can play around with it a little bit. And there's kind of ready-to-go versions of all of the audio effects, like for the EQ and the compressor, that's in this repo. So I encourage you to check that out as well, because you should be able to easily play around with those and maybe even fit them into your existing pipelines and other contexts, beyond style transfer. I also want to mention a few other works that you might be interested in related to this kind of differentiable signal processing theme. We also had some work on differentiable IIR filters, work on differentiable reverb, and also this paper here, which was doing differential EQ and compression. But in addition to this, we've also done a lot of work in neural audio effects, which I think would also be of interest potentially to many of the people here. So I'll share these slides as well so you can get all these links. But yeah, I just wanted to mention these other applications that I think some of you might be interested in and have some nice tie-ins with differentiable effects as well. Yep, and that concludes everything I wanted to talk about. So thanks so much, and happy to answer any questions.